Hi everyone. Welcome back to our series on AWS 3-tier architectures. This series is dedicated to equipping you with the knowledge and practical skills to design and implement robust, scalable, and secure applications on the AWS platform. We'll explore various approaches to building 3-tier architectures, starting with foundational concepts and progressing to more complex, production-ready solutions. Our goal is to provide a comprehensive understanding of the trade-offs and considerations involved in each architectural pattern. We've explored 4 distinct AWS-based 3-tier architectures so far. Our initial approach involved a straightforward setup utilizing 3 separate EC2 instances. This configuration hosted a React frontend served by Nginx on one instance, a Node.js backend managed by PM2 on another, and a MySQL database on the third. While simple, this approach presented limitations in terms of caching capabilities and handling increased workloads. Our second architecture introduced CloudFront to enhance performance. By caching static content at edge locations, CloudFront significantly reduced load times compared to our initial setup. This strategic placement of cached data led to a noticeable improvement in application responsiveness. However, while this approach effectively addressed caching concerns, it did not inherently provide a solution for handling fluctuating workloads. Our third architecture introduced an application load balancer to enhance scalability. By deploying 2 EC2 instances for the presentation tier and 2 for the application tier, we improved the system's capacity to handle increased load. To manage our application's data, we implemented an RDS MySQL database. This combination of ALB and RDS significantly enhanced the architecture's ability to handle higher traffic volumes compared to our previous solutions. Our fourth architecture introduced CloudFront to significantly enhance performance. By strategically caching static content at edge locations worldwide, CloudFront reduced latency and improved user experience. This combination of CloudFront, EC2 instances, application load balancing, and RDS created a robust foundation capable of handling increased traffic compared to our previous solutions. However, this architecture still lacked the ability to dynamically scale resources based on fluctuating demand. In this video, we'll introduce auto-scaling groups to our architecture. This feature will enable dynamic scaling of resources to match demand. During periods of high traffic, the auto-scaling group will automatically increase the number of instances to handle the increased load. Conversely, during periods of low traffic, it will reduce the number of instances to optimize costs. Additionally, we'll integrate CloudWatch to centralize application logs, enabling efficient troubleshooting, performance monitoring, and optimization. With CloudFront, application load balancers, auto-scaling groups, EC2 instances, RDS, and CloudWatch in place, we'll create a robust and scalable 3-tier architecture capable of handling fluctuating workloads while providing valuable insights into application performance. So, let's dive in and start implementing our 3-tier architecture. Let's break down the components of our high availability and scalable 3-tier architecture. We'll begin by defining the AWS cloud environment as the foundation for our solution. Within this environment, we'll establish a virtual private cloud to house our resources and ensure network isolation. To enhance fault tolerance and availability, we'll divide the VPC into 2 availability zones. Each zone will contain 3 subnets: a public subnet for the presentation tier, a private subnet for the application tier, and a private subnet dedicated to the data tier. For enhanced data durability and resilience, we'll implement a multi-availability zone RDS setup. The primary database instance will reside in first availability zone's second private subnet, while a standby instance will be deployed in second availability zone's second private subnet. This configuration ensures business continuity in case of failures or disruptions in the primary database. To dynamically scale our application tier to meet fluctuating demand, we'll implement an application tier auto-scaling group. This group will strategically manage EC2 instances across multiple availability zones, optimizing resource utilization. By deploying our application tier instances within this auto-scaling group, we'll enable the platform to automatically adjust capacity based on real-time requirements. Each EC2 instance will host our Node.js application, managed by PM2 for efficient process management. This approach empowers our application tier to handle varying workloads effectively, preventing performance bottlenecks and ensuring a seamless user experience. To manage and scale our presentation tier effectively, we'll implement an auto-scaling group. This dynamic infrastructure component will distribute presentation tier EC2 instances across multiple availability zones, ensuring high availability and performance. To securely access and manage these instances, we'll deploy a Bastion host outside the auto-scaling group. This Bastion host will serve as a controlled entry point to our private network, allowing us to manage and troubleshoot instances as needed. Each instance within this presentation tier auto-scaling group will function as a presentation tier endpoint, utilizing Nginx as a web server to deliver our React.js application to end users. To efficiently distribute traffic within our application tier, we'll implement an internal application load balancer. This load balancer will direct traffic across multiple EC2 instances within the private subnets. To manage external traffic, we'll deploy an internet-facing application load balancer, distributing incoming requests across the presentation tier instances. This two-tier load balancing approach enhances scalability and performance. To effectively manage domain name resolution and ensure secure communication, we'll leverage Amazon Route 53 for DNS management. By creating DNS records within Route 53, we'll map our domain to the appropriate resources. To establish secure HTTPS connections, we'll procure an SSL certificate from AWS Certificate Manager. This certificate will be integrated with CloudFront, our content delivery network, to encrypt data in transit and optimize content delivery to end users. With all components in place, users can securely access our application via HTTPS. Our database architecture ensures high availability through synchronous replication of data between primary and standby instances. In the event of a failure, Amazon RDS automatically transitions to the standby instance, minimizing downtime and data loss. To enhance observability and optimize resource utilization, we'll integrate CloudWatch into our architecture. Application logs will be centrally managed within CloudWatch logs, providing easy access for troubleshooting and performance analysis. CloudWatch alarms will be configured to trigger scaling actions within the auto-scaling group, ensuring optimal resource allocation based on demand. By scaling out during peak usage and scaling in during low traffic periods, we'll maintain cost efficiency while delivering consistent performance. Before we dive into implementing our three-tier architecture, let's take a moment to review the recent changes in our codebase for this setup. First, open the GitHub repository from the link provided in the description. Make sure to check out the branch, feature/add logging, since all the updates necessary for this setup are included there. Refer to the README file for the required bash commands. I've already cloned the repository and opened it in VS Code. Let's explore the Node.js project. You'll notice that I've added a new route called /health, designed to perform health checks on our application tier EC2 instances. Additionally, I've integrated application logging into each controller method. For logging, I've created a separate utility called Logger, which leverages the Winston library to generate application logs. Here's our application logs directory. It contains two log files, one for combined logs, which includes all logs except errors, and another dedicated to capturing error logs. To establish a foundation for our domain's online presence, we'll configure Route 53. This involves creating a public hosted zone that aligns with our domain name. A hosted zone serves as a container for DNS records, specifying how internet traffic should be routed for a particular domain. Once the hosted zone is created, we'll obtain the assigned name servers from Route 53. These name servers will then be updated at our domain registrar, directing DNS queries for our domain to Route 53. This process, which may take some time to propagate, is essential for routing internet traffic to our AWS infrastructure. To ensure secure communication and data encryption, we'll obtain an SSL certificate from AWS Certificate Manager. This process involves requesting and validating certificates for both the primary domain and any associated subdomains. AWS Certificate Manager will issue certificates for domains under our control. To validate domain ownership, we'll create specific DNS records within our Route 53 hosted zone. These DNS records serve as verification checkpoints for AWS Certificate Manager, confirming our authority over the domain. Once validation is complete, AWS Certificate Manager will issue the SSL certificate, enabling secure HTTPS communication for our application. To establish a secure and isolated environment for our application, we'll create a virtual private cloud. For this setup, we'll utilize two availability zones, each housing one public subnet and two private subnets. The public subnets will host our presentation tier, while the private subnets will accommodate the application and data tiers. To enable internet access for instances within private subnets, we'll deploy a NAT gateway in one of the availability zones. For simplicity, we'll omit VPC endpoints for S3 in this tutorial. Our VPC architecture will comprise two availability zones, each housing a public subnet for the presentation tier, a private subnet for the application tier, and a dedicated private subnet for the data tier. To streamline management and provisioning, we'll enable automatic assignment of public IP addresses to EC2 instances within the public subnets. This configuration simplifies access to instances while maintaining network security. To effectively manage network traffic and security, we'll establish a series of security groups. These security groups will define the communication rules for various components within our infrastructure. We'll create dedicated security groups for the Bastion host, presentation tier load balancer, presentation tier EC2 instances, application tier load balancer, application tier EC2 instances, and the database tier. By carefully configuring inbound and outbound rules for each security group, we'll establish a robust security posture for our application. Let's begin by setting up the security group for our Bastion host, which will serve as our gateway to the private resources within our VPC. It's essential that all security groups in this setup are created under the same VPC to ensure proper network configuration and communication between resources. For this demo, we'll configure the security group to allow inbound SSH traffic from any IP address, making it easier to access the Bastion host from anywhere. However, in a production environment, it's crucial to restrict SSH access to only a specific IP address or range of addresses to enhance security. Allowing SSH from everywhere in a production setting can expose your infrastructure to potential threats. Next, we'll set up the security group for our presentation tier load balancer. Since this load balancer is internet-facing, we need to configure it to accept HTTP traffic from any IP address, ensuring that users from around the world can access our application. It's important to note that for this particular setup, we won't be allowing HTTPS traffic directly through this security group. Instead, all HTTPS requests are handled by our CloudFront distribution, which acts as a secure front end for our application. By offloading HTTPS traffic to CloudFront, we can simplify our load balancer configuration while maintaining a secure and scalable architecture. After setting up the security group for the presentation tier load balancer, the next step is to create a security group specifically for the presentation tier EC2 instances. For this security group, we'll need to allow SSH traffic from the Bastion host, ensuring that we can securely connect to these instances via the Bastion host when needed. This setup is crucial for maintaining a secure and private connection to our instances. Additionally, we should allow HTTP traffic from the presentation tier load balancer. This rule is essential because all incoming internet traffic received by the load balancer will be forwarded to these EC2 instances in the presentation tier. This setup enables the proper routing of user requests to your application while maintaining security and organization within your network architecture. For the application tier load balancer security group, we need to allow HTTP traffic from our presentation tier EC2 instances. This configuration permits all inbound requests made to the backend from the front-end React application, ensuring smooth communication between the tiers. For the application tier EC2 instances security groups, we need to allow SSH inbound traffic from our Bastion host. This setup ensures that we can securely connect to these application tier EC2 instances via the Bastion host. Additionally, we need to allow inbound TCP traffic on port 3200 from the application tier load balancer. This configuration is essential because the load balancer will forward all incoming requests from the front-end React application to port 3200 on the back-end, where our Node.js application is running. This setup ensures seamless communication between the front-end and back-end of our three-tier architecture. For the data tier security group, we need to allow MySQL port 3306 inbound traffic from our Bastion host and application tier EC2 instances. This setup enables us to securely connect to our RDS instance from the Bastion host, which is crucial for tasks such as connecting a local MySQL workbench to the RDS instance via an SSH tunnel. This configuration ensures that only authorized sources can access the database, maintaining a secure and efficient architecture. Now, let's proceed with creating the Bastion host required for our setup. We'll name it Bastion host to keep things clear and organized. We'll stick with the basic, free tier eligible settings to keep the setup cost effective. If you haven't created a key pair yet, this is the time to either select an existing one or create a new one. This key pair is crucial as it will allow us to securely access our Bastion host later on. Next, we'll select the VPC and the public subnet where we want to deploy the Bastion host. This ensures that our instance is correctly placed within our network infrastructure. Finally, we'll associate the Bastion host with the security group we created specifically for it earlier. This step is essential for controlling and securing the traffic that can access our Bastion host. Once everything is set, we'll go ahead and create the instance. Now we'll set up the data tier for our architecture. We will be using an AWS RDS MySQL instance as our database. This service is highly scalable and provides high availability. In this setup, we will configure a primary database along with a secondary standby database. The standby instance will automatically take over as the primary database if anything happens to the original primary instance. Data will be asynchronously synced from the primary database to the standby database to ensure continuity and reliability. Next, we'll create a DB subnet group in the RDS console to define which subnets our RDS instance will use within the VPC. First, navigate to the RDS console and locate the option to create a DB subnet group. Let's give this group a meaningful name and a clear description that reflects its purpose in our architecture. From the list, select the VPC that we previously set up. Now, we need to choose the private subnets in each availability zone where we want our RDS instance to be deployed. This ensures that our RDS instance has high availability across different zones. After selecting the appropriate subnets, go ahead and create the subnet group. This step is crucial as it defines the network environment for our RDS instance, ensuring it's securely and properly distributed across multiple availability zones for resilience. Now we're ready to create our RDS MySQL instance, a key component of the data tier in our architecture. Given the requirements of our architecture, we'll be setting up a multi-availability zone RDS deployment to ensure high availability and resilience. First, head to the RDS console and begin the process to create a new database. For this setup, we'll choose the template labeled dev/test as our use case is for a POC project. Although we're not using the production template, it provides a balance between cost and functionality, which suits our needs. Note that the free tier template doesn't support multi-availability zone deployment, so we won't use that option. Next, select the deployment option as multi-AZDB instance. This ensures that our database will be automatically replicated across different availability zones, enhancing fault tolerance. Now, let's name our RDS instance and provide a master username for administrative access. For password management, select Manage Credentials Yourself, and make sure to set a strong master password and confirm it to secure the database. We'll leave the default configurations for the instance size and storage, as they are sufficient for this project scope. Next, select the VPC we created earlier to ensure the RDS instance is deployed in the correct network environment. Choose the DB subnet group we just created to define where the instance will reside within the VPC. Then, select the security group that we configured for the data tier to control access to the RDS instance. Finally, leave the remaining settings at their default values, as they are appropriate for this setup, and proceed to create the RDS instance. Now that our RDS instance is up and running, it's time to create a database and restore the data. To do this, we need to connect to our RDS instance via SSH. I've already included all the necessary commands in the README file, so you can refer to it for guidance. First, we'll open the terminal and execute the command to establish an SSH tunnel from our Bastion host to the RDS instance. This will allow us to securely connect our local MySQL workbench to the RDS instance. Once the SSH tunnel is established, we'll open MySQL Workbench on our local machine and create a new connection using the master username and password. After successfully logging in as the master user, we'll create a new user called App User specifically for our Node.js backend. This approach is a best practice, as it ensures that the master user credentials are not exposed or misused. You can refer to the GitHub repository for the SQL scripts needed to create this user, as everything is already provided. Next, we'll create a new connection in MySQL Workbench for the newly created App User and log in with the new credentials. Once logged in as the app user, we can proceed to restore our data to the database. As mentioned earlier, the necessary SQL scripts are available in the GitHub repository. Now that we've set up our data tier, let's move on to the presentation tier. In this step, we'll create a launch template specifically for our presentation tier. This launch template will be used by our auto-scaling group to automatically create EC2 instances as needed. After setting up the launch template, we'll create a target group and an application load balancer to manage the traffic directed toward our presentation tier. Finally, we'll establish our auto-scaling group for the presentation tier, ensuring it can scale in and out efficiently based on demand. To wrap up, we'll conduct stress testing on our EC2 instances to verify that the auto-scaling group responds as expected. Now let's create our presentation tier launch template. Start by giving it a clear, descriptive name. Provide a template version description so you can easily identify this version later. I'll enable the Auto-Scaling Guidance checkbox to help optimize the scaling of our instances. Next, select the Amazon machine image and instance type. I'll stick with the free tier eligible settings for this setup. Choose the key pair you plan to use for SSH access. Then, select the security group we created earlier specifically for the presentation tier. I won't select a subnet at this step, as we'll handle subnet selection when we create our auto-scaling group. For now, I'll leave the rest of the configuration options at their default settings. Scroll down to the User Data text box. Here, I'll add a bash script, which you can find in the GitHub repository's README file. This bash script will install Nginx. Start and enable Nginx to ensure it runs at boot. Fetch a metadata token and gather instance details such as the instance ID, the availability zone where the instance is running, and the public IP of the instance. Print these details to the index.html file, which will be displayed in the browser when you access the instance through the application load balancer's public endpoint. Finally, the script will restart Nginx to apply the changes. I'll paste this bash script into the user data text box and then proceed to create the launch template. Now let's create the target group for our presentation tier. We'll start by choosing the target type as instances. After that, we'll give the target group a proper name for easy identification. The protocol should be set to HTTP on port 80. Next, we'll select the appropriate VPC for our setup. For the health check, we'll add the endpoint as /health, which will be used by the associated load balancer to monitor the health of our instances. We'll leave the rest of the configurations as default and proceed to create the target group. Now let's move forward by creating an application load balancer for our presentation tier. We'll start by giving it a clear and descriptive name to ensure it's easily identifiable within our setup. This ALB will be internet-facing, meaning it will handle all external traffic directed toward our application. First, we select the appropriate VPC where the ALB will reside. Then, we choose the availability zones and corresponding public subnets that align with the target groups we're routing traffic to. This ensures high availability and redundancy across multiple zones. Next, we assign the security group we previously created for the presentation tier load balancer. This security group will control the inbound and outbound traffic for our load balancer, ensuring only the desired traffic is allowed. Finally, we associate the load balancer with the target group we created earlier. The target group contains the EC2 instances that will serve the incoming requests routed by the ALB. We leave the remaining configurations as defaults, as they suit our current needs. After reviewing the settings, we proceed to create the load balancer. Now it's time to create the auto-scaling group for our presentation tier. We'll start by giving it a clear and descriptive name that reflects its purpose within our architecture. Next, we'll select the launch template we created earlier. Since we haven't made any updates to it, we'll use the default version, which is version 1. After that, we choose the VPC and the subnets where we want our presentation tier EC2 instances to be deployed. It's important to select the appropriate subnets to ensure that our instances are distributed across multiple availability zones for high availability. Next, we'll configure the load balancer for this auto-scaling group. To do this, we'll click on Attach an existing load balancer and then select the target group we set up earlier. This will allow our auto-scaling group to automatically route traffic to the instances it manages. We'll also turn on load balancing health checks, which will ensure that only healthy instances are kept in service. Additionally, we'll enable group metrics collections with CloudWatch. This integration allows us to monitor the performance of our auto-scaling group in real time. Now we configure the desired capacity, minimum capacity, and maximum capacity for our auto-scaling group. The desired capacity represents the number of instances we want running under normal conditions. The minimum capacity is the lowest number of instances that should be running at all times, ensuring our application is always available. The maximum capacity is the upper limit of instances that can be launched to handle peak loads. Next, we set up the auto-scaling policy. We'll select the target tracking policy with an average CPU utilization of 50%. This means that whenever any of our EC2 instances reach a CPU utilization of over 50%, a CloudWatch alarm will trigger, signaling the auto-scaling group to launch a new instance to manage the increased load. With all these configurations in place, let's go ahead and create our auto-scaling group. Now, let's navigate to the EC2 console. Here, we should immediately see new EC2 instances being launched by our auto-scaling group. Since my desired capacity is set to 3, I can observe that 3 EC2 instances are in the process of launching. Once these EC2 instances are deployed successfully, we can proceed to access our application load balancer's public endpoint. This will allow us to verify whether the HTML page we configured earlier is being displayed correctly. If everything is set up properly, the page should load, showing the instance details we configured in the launch templates user data script. Now, let's test our auto-scaling group to ensure it's functioning as expected. To do this, we're going to manually increase the CPU usage on one of our presentation tier's EC2 instances. If the auto-scaling group is set up correctly, we should observe a new EC2 instance launching shortly in response to the increased load. First, open your terminal and connect to the Bastion host. From there, you'll connect to one of the EC2 instances in the presentation tier. After successfully connecting, we'll need to install the stress package on the instance to artificially generate high CPU usage. The relevant commands for this installation are provided in the GitHub README file. Once the stress package is installed, we'll start the stress test. You should see that the CPU usage on the instance spikes to nearly 100%. Next, navigate to the CloudWatch console and check the alarms. You should notice that the alarm high has been triggered, indicating high CPU utilization. This alarm will initiate a scaling activity within our auto-scaling group, causing it to scale out by launching a new EC2 instance. As expected, I can see that a new EC2 instance is already up and running, confirming that the scaling activity occurred successfully. If we revisit the CloudWatch console, we can see that the alarm high has already been addressed, meaning the scaling activity has completed. Additionally, it's worth noting that if we were to terminate an instance, the auto-scaling group would also trigger a scale-out activity to maintain the desired capacity of instances. Now, let's set up our application tier. We'll follow a similar process to what we did for the presentation tier. First, we'll create a launch template for the application tier EC2 instances. Then, we'll set up a target group that the application load balancer will use to route traffic to these instances. After that, we'll configure the application load balancer to distribute incoming traffic evenly across the application tier. Finally, we'll create an auto-scaling group to automatically adjust the number of instances based on demand, ensuring our application tier is always ready to handle the load. Now, let's create our application tier launch template. Start by giving it a clear and descriptive name so it's easily identifiable later. Provide a template version, and make sure to enable the Auto-Scaling Guidance checkbox to optimize it for scaling. Next, select the appropriate Amazon machine image and instance type that fits your application needs. Choose the key pair you plan to use for SSH access. Then, select the security group we created earlier specifically for the application tier. This security group will help manage the inbound and outbound traffic for these instances. Leave the rest of the configuration options at their default settings. Scroll down to the User Data text box. Here, we'll paste a bash script, which you can find in the GitHub repository's README file. To give you a quick overview, let me walk you through the script. First, we install Git to manage our source code. Then, we install Node.js and PM2. PM2 will manage our Node.js application processes, ensuring they stay up and running. Next, we define several variables within the script, such as the GitHub repository URL, the branch name we want to deploy, the directory within the EC2 instance where the repository will be cloned, and the path to the .env file. We navigate to the EC2 user directory, clone the repository, and check out the specified Git branch. After that, we navigate to the backend directory within the source code. We then define a variable for the log directory and create it within the EC2 instance. It's important to change the ownership of this directory to EC2 user to avoid any permission issues when generating logs. Following this, we create a .env file and add the necessary environment variables. Be sure to update these values according to your project's specific needs. This includes configuring your RDS endpoint, database username, password, and the database name. Finally, we install the necessary dependencies and use PM2 to serve the application. Once you've reviewed and confirmed the bash script, paste it into the user data field and create the launch template. This launch template will be the foundation for your application tier's EC2 instances, ensuring they are correctly configured from the start. Let's set up the target group for our application tier with a few important details. Begin by selecting Instances as the target type, ensuring that the traffic from the load balancer is routed to the individual EC2 instances within our application tier. Give the target group a clear, descriptive name that reflects its role in handling application traffic. Next, set the protocol to HTTP and specify port 3200, the port where our Node.js application is running. This setup ensures that the application load balancer forwards all incoming traffic to the correct port within the instances. After configuring the protocol and port, select the appropriate VPC where your application tier is deployed. It's essential to associate the target group with the correct VPC to ensure proper network routing. For health checks, add the endpoint as /health. This is a dedicated endpoint we've configured in the backend to monitor the health of our Node.js application. The load balancer will use this endpoint to periodically check the health of the instances in the target group, ensuring that only healthy instances receive traffic. Leave the remaining configurations at their default settings, which should be suitable for our setup. Once everything is configured, proceed to create the target group. To set up the application load balancer for our application tier, we'll begin by assigning it a clear and descriptive name that accurately reflects its function within our architecture. This load balancer is designed to be internal, meaning it will not be exposed to the public internet, unlike our previous load balancer, which was internet-facing. The internal load balancer will manage traffic within our VPC, directing it to our application tier instances. Next, we'll select the VPC that houses our application tier. It's crucial to ensure that the load balancer operates within the correct network environment. We'll then choose the appropriate availability zones, along with the corresponding private subnets, where our application tier instances are deployed. This step ensures that the load balancer can distribute traffic across multiple zones, providing better fault tolerance and availability. Assigning the correct security group to the load balancer is vital for controlling the traffic flow. We'll select the security group we created specifically for the application tier load balancer. This security group has rules that allow the necessary traffic while filtering out unwanted requests, ensuring that our application remains secure and performs efficiently. We will then associate this load balancer with the target group we created earlier. This association is critical, as it directs the load balancer to forward HTTP traffic on port 80 to the application instances running in our target group. Port 80 is standard for web traffic, and by specifying it, we ensure that our load balancer correctly routes incoming requests to our Node.js application. After carefully reviewing all these settings to make sure everything is aligned with our architectural goals, we will proceed to create the load balancer. This step will finalize the setup, enabling our application tier to handle internal traffic efficiently, with the load balancer distributing requests across the instances in our target group. Now, let's proceed to create the auto-scaling group for our application tier. Start by providing a clear and descriptive name for the auto-scaling group. Next, select the launch template we created earlier, ensuring that the default version, which is version 1, is chosen. Moving on, select the appropriate VPC and subnets where we want our application tier EC2 instances to be deployed. Configure the load balancer for this auto-scaling group by clicking on Attach an existing load balancer and then choosing the target group we set up earlier. It's important to enable load balancing health checks to ensure that traffic is only routed to healthy instances. Also, activate group metrics collections with CloudWatch to monitor the performance of our instances. Now, configure the desired capacity, minimum capacity, and maximum capacity for the auto-scaling group. These settings will determine how many instances the auto-scaling group will maintain and how it will scale based on demand. For the auto-scaling policy, select the target tracking policy and set the average CPU utilization threshold to 50%. This means that if any instance's CPU utilization exceeds 50%, CloudWatch will trigger an alarm, prompting the auto-scaling group to launch additional instances as needed. With all these configurations in place, proceed to create the auto-scaling group. Navigate to the EC2 console to check the status of our instances. At this point, we should see our Bastion host and 3 EC2 instances for the presentation tier up and running. Since we've configured the auto-scaling group for the application tier, we should also observe new EC2 instances being launched by this auto-scaling group. Given that the desired capacity is set to 3, you will see that 3 EC2 instances are in the process of being launched. Once these instances are fully operational, the next step is to verify that our backend Node.js application is running correctly. To do this, connect to one of the application tier's EC2 instances through the Bastion host. This will allow you to check the status of the Node.js application and ensure that everything is functioning as expected. Now that our application tier is running successfully, it's time to deploy our React.js frontend. To do this, we need to update our presentation tier launch template. Start by navigating to the launch templates in the AWS Management Console, selecting the presentation tier launch template, and clicking on Modify Template. Provide a descriptive version name to clearly identify this new version of the template. Scroll down to the bottom until you reach the User Data field. Here, we need to update the existing user data script with a new bash script, which I have provided in the GitHub repository. Please refer to it for the exact script. I'll walk you through the script step by step. First, the script installs Git, followed by Node.js and Nginx. Nginx is then started and enabled to ensure it runs on every boot. Next, we define variables for the repository URL, branch name, repository directory, environment file directory, API URL, and load balancer URL. It's crucial to provide the actual URL of our application tier load balancer here. The script then clones the repository into the EC2 user directory and navigates into the repository directory. It checks out the specified branch and moves into the front-end directory. Ownership of the repository directory is changed to avoid permission issues. A .env file is created with the API URL included, which is necessary for the front-end to communicate with the back-end. The script then installs all front-end dependencies and builds the React app for production. The build files are copied to Nginx's default directory to serve the front-end through Nginx. We then define the Nginx configuration file path in a variable, along with another variable for the server name, where you'll need to provide your domain and subdomain. The existing Nginx configuration file is backed up, and a new configuration file is created. Additionally, a specific Nginx configuration file for this application is created, where we update the server name, include the health check URL, and set up a reverse proxy to forward all /API requests to the application tier load balancer. Finally, the script restarts Nginx to apply all these changes. Once you've pasted this updated bash script into the user data field, quickly review it to ensure everything is correct, and proceed to create the new template version for our presentation tier launch template. Now, let's move forward and edit our presentation tier auto scaling group to utilize the latest version of our launch template. To keep things simple, I will set the desired, minimum, and maximum capacity all to 2. Since I've already demonstrated the auto scaling activity, there's no need to complicate this setup with more EC2 instances. We'll start by selecting the new version of the launch template. The remaining configurations can be left at their default settings. After that, proceed to update the auto-scaling group with the new settings. Once the update is complete, we need to immediately terminate the existing EC2 instances that were launched using the old version of our launch template. After the termination is successful, you should notice 2 new EC2 instances being launched by our auto-scaling group. When the EC2 instances are successfully launched, we can access our presentation tier load balancer's public URL to verify that our application is loading and functioning as expected. Since I've also configured backend logging for this project, I will perform some CRUD operations to ensure that backend logs are generated for these activities. Let's begin by connecting to one of our application tier's EC2 instances via SSH to inspect the generated log files. Once connected, navigate to the backend directory, and from there, go into the logs directory. Here, you'll notice that 2 log files have been generated. Let's open the combined logs file to examine the contents. In this log file, we can see that logs for the update and delete APIs are recorded, indicating that these requests were handled by this particular EC2 instance. Since our application tier consists of only 2 EC2 instances, it's likely that the create request was managed by the other instance. Now that we've confirmed the presence of our log files, it's time to integrate these application logs into CloudWatch logs. To achieve this, we first need to create an IAM role specifically for our application tier EC2 instances, allowing them to interact with CloudWatch. Next, we'll create a log group in CloudWatch logs where our application logs will be stored. Finally, we'll need to modify our application tier launch template to include these new configurations and then redeploy our application tier with the updated settings. Let's proceed to create the IAM role for our application tier EC2 instances. The purpose of this IAM role is to grant the necessary permissions for our EC2 instances to interact with AWS services, specifically for logging purposes. To get started, navigate to the IAM console and head over to the Roles section. Click on Create Role, and when prompted to select a trusted entity, choose EC2 as the service. After that, click Next to move to the permission step. Here, you'll need to search for and select two specific permissions. First, find the CloudWatch Logs Full Access permission. This permission allows our EC2 instances to write logs to CloudWatch, enabling us to store and analyze application logs in a centralized manner. Next, search for the CloudWatch Agent Server Policy permission. This policy is crucial because it grants our EC2 instances the ability to use the CloudWatch agent, which collects and forwards the logs and metrics from the instances to CloudWatch. Once you've selected these permissions, give the IAM role a clear and descriptive name that reflects its purpose. Finally, review all the configurations to ensure they are correct, and then proceed to create the role. This IAM role will now be attached to our application tier EC2 instances, enabling them to securely send log data to CloudWatch logs, where we can monitor and manage our application's performance and health. Now we create the log group in CloudWatch. Go to CloudWatch console and click on Log Groups. Click on Create Log Group button. Give a proper name for this log group. We will be using this log group name later in this video when we configure the application tier launch template. With this configs in place, create the log group. Let's proceed to modify our application tier launch template to integrate our application logs with CloudWatch logs. This step is crucial for monitoring and troubleshooting our application effectively. First, navigate to the Launch Template section in the EC2 console. Locate the launch template for the application tier, select it, and click on Modify Template. Start by providing a clear and descriptive version description to keep track of the changes you are making. Scroll down to the Advanced Details section, where we'll be making several important configurations. The first task is to select the IAM role we created earlier from the IAM Instance Profile dropdown. This role is essential because it grants the EC2 instances the permissions needed to interact with CloudWatch, allowing the instances to send logs and metrics securely. Next, enable detailed CloudWatch monitoring. This feature is important because it allows us to collect more granular metrics from our EC2 instances, which can help in gaining better insights into their performance and health. Detailed monitoring provides data points every minute, compared to the default 5-minute intervals, enabling quicker and more precise responses to any issues. Scroll down to the bottom of the page to the User Data field. Here, we will modify the bash script that was previously added. You can find the updated script in the GitHub repository's README file. I'll walk you through the changes. The new section of the script focuses on configuring the CloudWatch agent, which is a vital tool for collecting and sending logs and metrics from our EC2 instances to CloudWatch. The first command in the script installs the CloudWatch agent on the EC2 instance. The CloudWatch agent is a software component that allows us to collect system-level metrics and application logs from our instances and send them to CloudWatch. Next, the script configures the CloudWatch agent by defining the file paths for the logs we want to monitor, specifying the log group name, and ensuring that this name matches the log group you created in the previous step. You'll also need to give a unique name for the log stream. For simplicity, we'll use the instance ID as the log stream name. This helps in identifying which instance is sending which logs. Additionally, the script sets the timestamp format to ensure logs are recorded accurately. Finally, the script starts the CloudWatch agent, which begins collecting and sending the logs as per the configuration. Once you've reviewed and confirmed the changes, copy the entire updated bash script and paste it into the user data field of the launch template. After verifying everything is in order, create the new template version. With this setup, our application tier EC2 instances will be capable of automatically sending logs to CloudWatch logs, making it easier to monitor the application and diagnose any issues that may arise. Let's update the auto-scaling group for the application tier. Choose the correct version of the launch template that we've just updated. Keep the other configurations as defaults and proceed to update the ASG. Once the update is successful, we need to immediately terminate the existing application tier EC2 instances so that the new instances can be launched using the latest version of our launch template. After a short while, you should observe 2 new EC2 instances being launched by the ASG. Once the new instances are up and running, we can test our application by accessing it through the presentation tier load balancer URL. To verify that the logs are now being captured by CloudWatch, perform some CRUD operations via the front end. After executing these operations, navigate to the CloudWatch console and explore the log group we created earlier. You should see 2 log streams corresponding to the 2 EC2 instances in the application tier. By opening each log stream, you'll find the logs for the requests we sent from the front end. Since this setup is highly available and we have 2 EC2 instances for our Node.js application, requests are distributed across both instances. Therefore, logs related to different requests will be present in both log files, not consolidated in a single log file. To review all the logs, you should check both log streams. To optimize content delivery for our application, we'll set up a CloudFront distribution. The origin for this distribution will be the application load balancer we previously created, configured to use HTTP. To ensure a secure connection, we'll configure CloudFront to automatically redirect all HTTP traffic to HTTPS. To keep the setup straightforward, we'll disable the web application firewall and limit the number of edge locations, which will streamline the deployment process. Next, we'll add our domain and subdomain as alternate domain names, ensuring they are correctly pointed to the CloudFront distribution. We'll use the SSL certificate we obtained earlier to secure these connections. Once we've configured these settings, we'll proceed to create the CloudFront distribution. It will take some time to deploy across the selected edge locations, but once it's complete, our content delivery will be optimized for both performance and security. To ensure that traffic is properly routed to our CloudFront distribution, we'll set up DNS records within the Route 53 hosted zone we established earlier. First, we'll create an alias record for the root domain, directing all traffic to the CloudFront distribution. Then, we'll create a second alias record for the subdomain, ensuring that this traffic is also mapped to the same CloudFront distribution. By configuring these DNS records, we'll seamlessly route traffic from both our root domain and subdomain to the optimized CloudFront distribution, enhancing our application's performance and security. With everything now set up, we should be able to access our application using both the root domain and the subdomain. Let's go ahead and perform some CRUD operations to ensure everything is functioning correctly. After testing, we'll navigate to CloudWatch to review the logs. We should see entries corresponding to each action we performed on the back end, confirming that our logging and application setup are working as expected. To wrap things up, we've successfully set up a fully functional and highly available 3-tier architecture on AWS. We began by configuring the data tier with RDS, then moved on to the presentation and application tiers. We integrated logging with CloudWatch, optimized content delivery using CloudFront, and routed traffic through Route 53. Finally, we validated our setup with some CRUD operations, ensuring that everything works seamlessly. I hope this guide has been helpful in understanding the steps to deploy and manage a robust AWS architecture. Alright everyone, that's all I have for today. I hope you found this video helpful in the context of cloud computing. See you next time with another exciting topic. Leave a comment below with any questions you have. Don't forget to subscribe for more exciting tutorials. I've also included a link in the description below to a detailed article about this topic.